Alright, looks like in this pre-class problem we're given two sources for magnetic fields. Anytime we have a current carrying wire that acts as a source for a magnetic field. And we know right off the bat that we're going to have to use the principle of superposition. Superposition is just a fancy word for adding vectors. Whenever we have multiple sources for a magnetic or an electric field, we have to add vectors because the field is a vector quantity. So in this problem, let's find out what they're asking us to find. So they give us the current going in through I1. They say I1 equals 5 amps. They give me those distances, the radius of our circular loop, and the distance between our circular loop and the straight wire. And then they ask me what must the second current be, this I2 current, so that the net field at point P, the location P is right in the center of that circular loop. We want that net field at location P to be 0. Alright, so first step in adding vectors is to figure out, well, what are the direction of those two vectors? So to figure out the direction of the magnetic fields created by each of these sources, we have to use the right-hand rule. So starting with source 1, if we do the right-hand rule, we find that the magnetic field created by this source points into the page down here. And we'll call this B1. Then if we do the right-hand rule again for this second source, which is the circular loop of current, we find that this creates a magnetic field that points out of the page right there at the center of the loop. And we'll call this the second magnetic field. Alright, so once we figured out the direction, now that will give us an idea of whether we should make these magnitudes of these two fields positive or negative, whether they're going to add together or subtract from each other. Alright, so let's mathematically write how we're going to find the net field. So we have the net field, it equals the sum, the vector sum, of the other two fields. And so we're just looking at the magnitudes, but let's look at field 1. We see that it points into the page, so let's say that that has a negative direction, right? And then we're going to use this equation to describe its magnitude. The reason we know we can use this equation is because this is the equation for the magnitude of the magnetic field created by an infinitely long, perfectly straight wire, which I1 kind of fits that definition based on the information we're provided with. So that's our first magnitude. Now we have to add to it the magnitude of the field created by our second source. And I'm going to say this is pointing in the positive direction. It's coming out of the page. So I'm going to use another equation, different equation for this, because this is no longer an infinitely long straight wire, but now we're looking at the field at the exact center of a perfectly circular loop of current. And this loop of current has a radius of big R, as they give us in the problem. So it's important to recognize what these two different R values are. The R is the distance from the source to the location of interest. So in this second case, the distance from the source to the location of interest, because it's at the center, is everywhere just as capital R. For the first source, the infinitely long straight wire, the distance that our point is from that is actually this big R. So we'll write this to the side here. The distance from the straight wire to the point of interest, location P, equals big R plus that little distance D. Alright, so let's just keep that in mind, and we'll have to use that at the end when we plug in for value. We're asked to solve for when the net field at the center of that loop equals 0. So if I set this B net equal to 0, I can do some simple algebra. I'm just going to add this term to both sides because it's going to help me solve this problem a little bit cleaner. Right? So now I have this term equals, so the magnitude of the field created by the first source equals the magnitude of the field created by the second source. Right, so this is our criteria to get them to cancel out and end up with a net field of 0. So an easy step we can do is cancel out like terms on both sides. So I've got a mu naught on both sides. I've got 2 on both sides. Now I just need to solve this equation for I2. So if I multiply both sides by capital R, I end up with an expression that looks like this. Alright, so we've done all the hard work now, and the last step is we just need to plug in values to solve for what this current is. So in the problem, we're told that this big R is 8 millimeters. So don't forget to convert that to SI units. And we're told that the first current is 5 amps. Alright, and then we have pi times the second distance, which we remembered is the D plus the capital R. Alright, so the capital R is 8 millimeters, and then my D is 3 millimeters. That equals my second current. So if I plug in all those values to my calculator, I end up with the second current equals 1.16 amps. So with that much current flowing through that circular loop, we end up with zero net magnetic field at the center of the loop.